So this is a practice exam from 2018 at Concordia, and we're going to start off with the short answer questions. In these questions, they usually want you to draw an image or a graph, write a sentence, maybe write some equations, but it's not supposed to be too lengthy. So pause, try your best to answer them, and if you're struggling, see the chapter that I point to. So question 1 says, Gauss's law of magnetism states that the flux through a closed surface is zero. Why? This is the equation that we're looking at here, where the key difference is that we have this little circle here. A closed surface would be something like a sphere or a cube. A circle is not a closed surface. A straight line, not a closed surface. So to answer this, let's remind ourselves about electric flux. Back then, we had, say, a positive charge, and we looked at our electric field lines, and we draw them like this, going radially outwards in 3 dimensions. If we were to draw a closed surface, so a sphere, around this charge like this, and we were to count how many lines are going out, how many lines are coming in, we see we have a net flux out through that closed surface. So we do have a flux, right? This is very different when we have magnets. And the key word here is dipole. Magnets are dipoles, meaning that they always have a north and a south side. You can never just have a north or just have a south. When we draw our field lines, they go out of the north and back in to the south. So they always come back. And you can think of this drawing as being like 3-dimensional as well. If I were to draw a closed surface, so a sphere around this, say like this, and I would ask myself, what is the net flux? I'd count how many lines are going out and how many lines are coming back in. So if I do that, I see I have north going, I think I drew that a little weird. So I have the north line coming out, but then it's going back in. Down here, it's going out, but then it always goes back in. And that's the issue when we have magnets, is that there cannot be a net flux because there's always a north and there's always a south, so whatever goes out has to go back in. Some of you might be wondering, well, why is the magnetic flux not always zero? Remember that this is not a surface integral. It's just a normal area integral. So for instance, maybe I have my magnet, I'll draw it again, the north and the south, and I have my field lines like this, and maybe I draw a circle just like around here. So think of it as like looping around that field line. And then I look at how many field lines are coming in versus going out. It's a little bit weird because it's just a circle. It's 2-dimensional. And so I just have field lines going through it in this one direction. So there is a net flux. But remember, when we're talking about closed surfaces, we have to draw a sphere. And whenever we draw a sphere, it's going out, but it's always coming back in. So that's it for that question. And we're going to move on. In 2, you're asked, if we charge 2 capacitors, C1 and C2, disconnect them from the battery, then connect them with opposite polarities, what happens to the energy stored in the system? You might not be given these drawings. I'm providing them for you just to kind of help you along your way. But what I find people have the most difficulty with is this, connecting them with opposite polarities. What I recommend you do is first draw out a normal circuit with C1 and C2 and think about where the charges pile up. So here we have our battery. We'd expect the positive charges to be here and to be here, right? Maybe the capacitance of C1 is very high. Capacitance is the capacity of the capacitor to carry that charge or to hold that charge. So maybe there's like 1,000 charges here and only 10 here. Doesn't really matter. But it's going to be positive here, negative, and negative. What they mean by connect them with opposite polarities is not flipping both of them. It means connecting them such that the positive and the negatives are connected to each other. So I draw that out here where I take this one and I flip it upside down. So its negative side is here and its positive side is here. To answer this question, which deals with energy, we need to know our energy equations. Hopefully you're provided with your equation sheet. So you know that the electric potential energy of the electric field is 1/2 Q squared over C. See the capacitance, it doesn't change. But what does change is Q, where Q is how much charge is stored on your capacitor plate. Here I drew 4 and 4. You have to think about these attractive forces now because they are charges. I have positive and negative. they feel an attractive force to one another. So for instance, maybe my positive charge here, it's gonna go down here and cancel out with this negative charge. So now there's no net charge. Those charges still exist, sure, but there's no net positive or net negative. Same thing for this one. It feels this attractive force and it cancels its net charge out with another one. So Q is going to decrease, and because Q decreases, UE decreases. Okay, so if you're struggling with this, go see chapter 25 that talks about capacitors. 3 says, what is the effect of the inductor on the current in an RL circuit with DC current after the switch is closed for a long time? So the idea here is that the switch is open, and when the switch is open, it means I is equal to 0. Switch is closed, well, I increases as it's E over R, 1 minus e to the negative t over tau. So remember, when we have an inductor, it's kind of like that water wheel, where it's reacting to the change in current, but once the current reaches a steady state, it itself has nothing to react to. So what I mean by that is here, this is our graph. We have current with respect to time, and then we have time. If there was no inductor, the switch would turn, close, and we'd have current, and the current would immediately increase to its maximum value. When we have an inductor, it takes some time to increase, but eventually it does reach its maximum value, and it stays there, where its max is E over R. So when it says here, the switch is closed for a long time, it's talking about this region here. So the answer is, what is the effect of the inductor on the current? Nothing. It's not affecting the current at all, because it's just acting like a normal wire at that point, and it's not causing any pushback. We're going to move on to 4. It says a permanent magnet is dropped and passes through a circular loop, north pole first. What is the direction of the induced current in the loop as the magnet A approaches the loop and B goes away from the loop? This is chapter 30, so Faraday and Lenz's law. You can draw this 2 ways. You can pretend that you're dropping it to the right. I don't love that. I would prefer to draw it out like this, because it's more of a physical, I'm dropping it. Also, I find that it makes it easier to figure out clockwise and counterclockwise, because I look at this circle that I drew here, and it does not look very, very clear. It's it kind of looks like it's in the XY plane. Regardless, this is our situation. What I recommend you do is draw the magnetic field lines for either the north or the south. Don't draw them for both. So I'm going to draw them for the north, and my field lines are going like this, right? So what I have is I have the field lines from the North Pole going downwards into my loop. When the magnet is way down here, there are no field lines. When the magnet's down here, there's a lot of field lines going down. I know that my induced current is going to be such to generate a magnetic field that opposes that change. Opposing the change means generating a magnetic field pointing straight up. This is V. Using my second right-hand rule, I know that my current has to be counterclockwise to be able to generate such a magnetic field. If you don't remember, point your thumb in the direction of B and wrap your hands around that coil, that loop, and you're going to see that your knuckles curl in the counterclockwise direction. So now that's A, but B says, what is it when the magnet is going away from the loop? So it's down here at the bottom and it's descending. My magnetic field lines for the North Pole are still going down, but essentially I had magnetic field lines going down, and when the magnet's way down here, I have less magnetic field lines going down. The current is again going to be such to compensate that change, and it's going to induce a magnetic field in that down direction as well. And if I use my right hand rule again, I point my thumb in the direction of B, I wrap my hands around, I see that the current has to be clockwise. Okay, so counterclockwise and then clockwise. We're going to enter the long problem section. So in these, you're usually expected to actually get a numerical answer, and you're expected to be a little bit more rigorous with your use of equations, right? So actually write out all of your steps and don't just jump to the final answer. Here you have a charge of 2 microcoulombs with a mass of 100 grams. It's suspended, making a right angle of 30 degrees, so an angle of 30 degrees with the vertical line, like so. You're asked to figure out the sign of the charge and then the magnitude of the electric field. The sign of the charge comes from the fact that the electric field is pointing to the right and my mass is also going to the right. I know that it's positive charges that move in the direction of the electric field, so that means that this charge has to be positive. So that's it for A. But then B is saying, what is the magnitude of the electric field? To do that, we need to figure out all of our forces involved and then say that the forces along the x direction have to cancel each other out because it's not moving, and the forces along the y direction have to cancel out because, again, it's not moving. So what forces do we have? Well, we have gravity going down. We have the electric force pushing it to the right, which we can write as Q times E. And then we have the tension going up like this. We're going to divide the tension up into its x and y components. So here, this is its x, which is going to be T sine of 30. And then here we're going to have T cosine of 30. So I'm going to put that into my free body diagram where I have Q, E, T sine 30, T cos 30, and then mg. I know that T cos 30 has to be equal to mg because in the y direction everything has to cancel. So I'll just write that here, y hat. And then x hat, I have T sine 30 is equal to QE. I want to figure out what E is, so that means I need to know what T is. To do that, I just isolate for it, where I have T is equal to mg divided by cosine of 30. I then plug this answer here, and I get mg sine 30 divided by cos 30 times q is equal to E, and just divide a q on both sides. So this is your final answer. Of course, now we can actually plug in some numbers. We get E is equal to the mass we were told was 0.1 grams. We know G is 9.81 meters per second squared. We have sine 30 divided by cos 30, which is going to be square root of 3 over 3. If you have access to calculators, you can just plug that into. And then Q is positive 2 times 10 to the negative 6 coulombs. And that is going to give you something like square root of 3 over 6 times 10 to the 6 newtons per coulomb. The most important thing I find is really just getting to this equation, because from then on, you're just plugging numbers in. So I don't know if I mentioned it, but if you're super lost, go to chapter 22 and look at that. Okay, so this one I find a little bit trickier, but definitely doable. You have a uniformly charged rod with a total charge plus Q, length L, and linear charge density lambda. You want to know what the electric potential is at points A and points B. To do that, you can go see chapter 23 for the equations, or hopefully they're provided for you. And so what we're going to do is figure out, well, what is the potential at point A due to a little chunk of charge dq here. So this is dq. I know my equation is going to be dVA is equal to KE dq over RA, where RA is just the distance from A to my little chunk of charge. So what I'm going to do now is figure out how to integrate it such that I add up all of these little charges and all of their contributions at point A. I'm going to define this point here in the middle as x is equal to 0. I'm then going to define x as being the distance from x is equal to 0. So for instance, down here, this is L over 2. X is equal to L over 2 because this has length L over 2. This point here is x is equal to negative L over 2. So what I'm going to do then is say, well, this space between my little piece of charge dq and my center point here, this I'm going to call x. So that means that RA is going to be equal to the square root of x squared plus h squared. And then dq is equal to lambda times dx. And x ranges from negative L over 2 to L over 2. I can plug everything in together and write out my integral, where I get VA, the potential at point A, is equal to ke lambda, the integral from negative L over 2 to L over 2 of dx over square root of x squared plus h squared. Okay, so that is the integral. Maybe you know how to solve this, maybe you don't. I know that some professors don't put a huge emphasis on the integration part, like the math part of physics, so you might be given this as a solution. I'm going to be assuming that you are told what this integral is in some way, so we're going to stop there. Do remember that the potential is a scalar quantity, so it's just going to be a number. It's not pointing in any direction. We're going to do the same process now to figure out what VB is. Here, it's the same idea, where let's consider this little green chunk of charge now. The distance from B to this chunk of charge dq is RB. We have a little bit of a problem now, because I want to know what this distance is, because I need that distance to be able to figure out what RB is. But I've defined this to be x. So if I know this whole thing is L over 2, then the one in blue, so I just put in blue now, is going to be L over 2 minus x. Because I want to be consistent in both of my equations, I've defined x to be something, like x is how far is it away from the center to my charge. And that's super good when I have A, like I want to figure out VA, but it's not as useful when I want to figure out VB. So I'm just going to have to take L over 2 minus x to get this region. There are different ways to solve this problem, and if you want to use those, be my guest, but this is just how we're going to solve it here. VB is then equal to ke lambda integral from negative L over 2 to L over 2 dx over, and instead of saying x, we're going to say L over 2 minus x squared plus h squared. So again, I'm going to assume that you are actually given this integral and you get a number. So then to figure out the work done to move a charge q from A to B, you need this equation. You just figured out VA and VB. Let's say you're given what the charge is. Well, then you just plug it in and you get a number, right? So I have some number for Q, I put it in. I have some number for VB minus some number for VA, and that is the work done. So it's not a hard second question. Okay, so this is question 3. It says, consider the circuit branch and determine C equivalent between points A and points B. So what I want to draw your attention to is A here, it's a straight line, a wire, and then there's a circle. This means that it's connected to a battery, and same thing for B. So here we have our battery, like this. They just didn't want to draw it. To find C equivalent, we need to know how to add up our capacitance when they're in series or when they're in parallel. So C equivalent when they're in parallel is equal to C1 plus C2 plus dot dot dot. When they're in series, C equivalent is equal to 1 over C1 plus 1 over C2 plus whatever to the power of negative 1. Hopefully you notice here, these are in parallel and these are in parallel. So that means that this is going to be 10 microfarads, 10 microfarads, and 10 microfarads. These are all in series. I add them up and I get 10 over 3 microfarads. So just to remind you, I use this equation here, and then that's what I get for the equivalent capacitance. I always do recommend that you start off with your circuit and go step by step, simplifying it out, and not to go from here to here, because it's going to make the next question harder. The next question being, if we connect a 10-volt battery between A and B and let time go to infinity, how much energy is stored in one of the 5 microfarad capacitors? So we have a bit of a problem. We know delta V across the whole thing, but we don't know delta V across one of the 5 microfarad capacitors. So what we're going to have to do is start here, figure out what C, delta V, and Q are, and then take some value back with us here, figure out all 3, and then go back here. So the equation between C, Q, and delta V is this. It's Q is equal to C delta V, and we're going to start using it. What I mean by that is here, This is our equivalent capacitance, right? So like at the end, we got C equivalent was equal to 10 over 3 microfarads. And we know that delta V, the potential across it, is 10 volts. I know C, I know delta V. I apply this equation and I get Q is equal to 100 over 3 microcoulombs. Now I have to decide which of these two values, Q or delta V, can I take back with me and apply to any of these 1 capacitors that are in series. The answer is Q. So the charge on this capacitor, the equivalent capacitor, is equal to the charge on this one, or this one. So like all of them have the same charge. So let's look at this capacitor here. I now know that its capacitance is equal to 10 microfarads, and the charge on it is 100 over 3 microcoulombs. I know C, I know Q. I can use this equation here to figure out what delta V is. So delta V is equal to Q divided by C is equal to 10 over 3 volts. So now I know the potential across this capacitor here, and I have to think, well, this here is this, and it came from this, where these are in parallel. So if I know everything there is to know about this capacitor, what applies to these capacitors? And the answer is the potential difference. The potential difference across this 5 microfarad capacitor is equal to the potential difference across its equivalent capacitor. So then I take delta V, and I have delta V is equal to 10 over 3 volts. C equivalent for one of them is equal to 5 microfarads. So I know delta V, I know C, I know Q, and then I can figure out what the energy stored on one of these capacitors is. It will be UE is equal to 1/2 C delta V squared, which is going to be equal to 1/2 times 5 microfarads times 10 over 3 volts squared, which is going to be 5 over 18 times 10 to the negative 4 joules. Again, it's really just getting all of these values here and then knowing what equation to use, plugging everything in, and getting something. So that is that. I have done a very similar video on this, but again, go back to chapter 25 and it's talked about there. This one I find quite a bit easier. All we have to do is calculate the currents 1, 2, and 3. Everything's drawn out for us. All we have to use are Kirchhoff's loop rules and Kirchhoff's junction rules. So let's pick a junction. I've chose this one here in green. You could also choose this junction here, it doesn't matter. And let us now figure out what currents are coming in and what currents are coming out. So junction rule. I1 is coming in, I3 is coming in, I2 is going out. So that means I1 plus I3 is equal to I2. Let's now look at loop 1. I drew it like this. Usually you want to draw it starting at some battery and then following where you think the current is going like this. We then have to add up all of the potential gains and losses. So here we have 10 volts. So 10 volts minus, here we have a potential drop of I1 times 3 kiloohms. So I1 times 3 kiloohms plus 4 volts from this second battery minus I1 times 2 kiloohms. Because if the current here is I1, the current here also has to be I1 because like there is no junction to change it. So minus I1 times 2 kiloohms is equal to 0. So that means 14 volts minus I1 times 3 kiloohms plus 2 kiloohms is equal to 0. So 14 volts minus I1 times 5 kiloohms is equal to 0, or I1 is equal to 14 volts divided by 5 kiloohms. You know, if you want to actually write that in amps, you could just say this is equal to 14 over 5 times 10 to the minus 3 amps. And that's I1. Let's look at loop 2 now. Where loop 2, we have 4 volts minus I3 times 2 kiloohms is equal to 0. I isolate for I3 and I get I3 is equal to 4 volts over 2 kiloohms, which is equal to 2 times 10 to the negative 3 amps. So I know I3, I know I1 and I know how they're related via the junction rule, so I just have to add them up together. I2 is then equal to, we have 14 over 5 times 10 to the negative 3 amps plus 2 times 10 to the negative 3 amps. And that is going to give us something like 4.8 times 10 to the negative 3 amps. And that is it for this question. We're going to move on here. This one, I definitely find a little bit tricky because I know some of you haven't really worked with these type of equations before, or this type of question, but it is definitely doable. We have two infinite wires parallel to one another, both carrying a current of magnitude I. Find B, the magnetic field at O, where O is just this point here that I colored. So to do that, we need to think about, well, what is a magnetic field caused by one infinite rod? And that's going to be B is equal to mu naught I over 2 times pi times r, where r is the distance from your wire to your point. So this is r. And what we see here is that r is the same for wire 1 and wire 2. So this is r1 and this is r2. Now the tricky thing is figuring out where the magnetic field is pointing. So I want to remind you of your second right-hand rule, where here this is saying the wire is coming out of the page. So point your thumb in the direction out of the page and wrap your hands around. And you see that your hands, your knuckles anyways, are going to be curling in this direction. Right, so you point your thumb out and wrap your hands around. That means at any point here, the magnetic field is pointing tangential to this curve. If I were to then draw a line from my wire to this point here, I notice that, well, that's 90 degrees. So that's 90 degrees. This is 90 degrees. It's always 90 degrees because they are always perpendicular to each other. So this is R and this is B. The same applies here, where at this point, B1 is going to be 90 degrees like this. And then B2, well, it's going into the page instead, so it's just going to be pointing in this direction, but still with 90 degrees. So now the trick is, I should write that's B2. Now the trick is figuring out how to add up B1 and B2. They have the same magnitude, so I do this a little bit wrong, but like they should be pointing in equal and opposite directions, just with the same like angle like this. Anyways, so we need to figure out how much of B1 is in the x direction, how much of B1 is in the y direction. So if I try to zoom in a little bit more, I'm going to draw like this and say, well, what is this angle here? Hopefully you remember this from, I guess, trigonometry, that if that is 60, this is 60, and then if this is 90, this is 30. So I'll do it again on this side, where we know that this is 90, this is 60, which means this is 30. So that means that B1 in the x direction is equal to B1 cosine of 30. B1 in the y direction is equal to B1 sine of 30. And similarly, we have B2 in the x direction. It's B2 cosine of 30. And then here we have B2y is equal to B2 sine of 30. Now something that you do have to realize is that this 30 degrees, well, it's in the opposite direction of this 30 degrees. By that, I mean that B1x is pointing in equal and opposite directions as B2x. So that means that they cancel out. So B1x is equal to negative B2x. So that means B net is equal to 0 in the x hat direction. In the y hat direction, however, we have B1y is equal to B2y. So B1y is equal to B2y. So that means B net, where we're just adding up the y components, is going to be 2 times B1y. You could also say 2 times B2y. It doesn't matter. And so then if we write that out, we have B net is equal to 2 times, what is B1y? It's this. What is B1? It's this. So then it's going to be 2 times mu naught I over 2 pi r times sine of 30. The sine of 30 is 1/2. So it's going to be that times 1/2, cancel that, and I get B net is equal to mu naught I over 2 times pi times r. This sometimes shows up as a multiple choice question if you have this exact scenario where they're separated by 60 degrees and you want to find this magnetic field at this point here. All you have to do is remember that the net magnetic field is literally just the magnetic field of an infinite wire pointing straight up. We're going to move on now to 6. This one's also a little bit easier. You have an RL circuit and S is open for t is less than 0, then close at t is equal to 0. You're given L, R, and E. What is I at t is equal to 0.05? So this corresponds to this graph here, right, where we have I of t, we have the current starting at 0 and increasing, and we know what the equation relating to this is from chapter 31. So it's just I of t is equal to E over R 1 minus e to the negative t over tau, where tau is equal to L over R. So that means I of t is equal to E over R, which is 10 volts divided by 10 to the negative 2 ohms, times 1 minus e to the, then we have negative, t is 0.05 seconds, times, and then tau, which I'm going to write that here. Tau is L over R, which is 10 to the negative 3 henries, divided by the resistance of 10 to the negative 2 ohms, which is 0.1 seconds. So it's t divided by 0.1 seconds, and if you add everything up, you get 390 amps. So this question is really just about remembering what equation to use and how to just plug all of these numbers into it, but that's it. The next one gets a little bit more tricky again. You have an RLC circuit with I of t is equal to 5 amps sine 100t. You are asked to figure out what delta Vs is, the voltage across the source. So this is chapter 32, and if you remember from that chapter, this is what we got here, where whenever we have this type of circuit, we have a potential drop across R, across L, and across C. We know that the potential across the source is equal to the combination of all of these potential drops, so delta V max here. So we're essentially figuring out what is delta V max, but also what is phi, which is the phase difference between the current and delta V max. So essentially, you have to kind of realize that you are told a lot implicitly, well, not explicitly. So here in the current, you're told what I max is. I max is equal to 5 amps. You're also told what omega is. Omega is equal to 100. So from there, you have the equations delta V max is equal to I max times Z. And you know that delta Vs, the potential across the source, is equal to delta V max sine omega t plus phi, where phi is equal to the inverse tan of XL minus XC divided by R. So you just need to pull all of these equations out, calculate everything, and then shove them back into delta Vs. We're going to go ahead and do that. So delta V max is I max times Z. What is Z? Z is the impedance, and it's equal to R squared plus XL minus XC squared to the 1/2. What is XL? XL is the inductive reactance, and it's equal to omega times L, where omega is 100. L is 5 times 10 to the negative 3 henries. And this has units of ohms, so 0.5 ohms. XC is the capacitive reactance, and it's 1 over omega C is equal to 1 over 100 times 5 times 10 to the negative 3. And then we have units of farads. This is going to be equal to, if I did that, it's 2 ohms. Okay, so we know XL, we know XC, we know R, the resistance. Plug all that in together, and you get Z is equal to 1.58 ohms. So you have a value for the impedance. We can also plug in our numbers to phi, the phase, and we get 10 minus 1. XL is 0.5 ohms minus 2 ohms divided by 0.5 ohms. And then phi is equal to negative 1.25 rad. Okay, so you have phi, you have Z. You can then write delta V max is equal to I max, which is 5 amps times 1.58 ohms. And then here, phi is negative 1.25 rad. And then omega is 100. So if you write that out as a nice equation, you get delta Vs, the potential across the source, is equal to 5 amps times 1.58 ohms, sine of 100t minus 1.25. Okay, so that is it. The negative sign here is just saying that delta Vs is lagging behind Imax. But that's about it. So in B, you're asked, what is the voltage across both the resistor and the inductor? You're essentially going to do the exact same thing you just did, and then just take out the capacitance. So here, it's like we have a voltmeter attached here. And so we're only considering the potential drop of this and the potential drop of this, not the capacitance. So what I mean by that is, well, it's going to be similar. So delta VRL is equal to, then we have delta V max, we're going to call it prime because it's a different value than it was last time, sine of omega t plus phi prime. Delta V max prime is equal to I max times Z prime, where Z prime is just equal to the square root of R squared plus, remember how we had XL minus XC squared? Well, there is no more C. So it's just going to be XL squared, like that. And then phi prime, we just take out any mention of the capacitance, so it's going to be the inverse tan of XL over R. So you can go ahead and do that yourself, where you just plug in your numbers, get some value, plug it in here, and then plug it into this equation there. Okay. So we're going to move on. 8, it says you have an infinite wire carrying a current I and a square loop of wire sitting S away from it. So if we draw that out, this here is S, and it has a square loop. I don't know if it says it, but this here is also S, and this is S. So everything is S. Initially, the current is equal to 0 in the loop. You cut the infinite wire. Explain why a current is induced and in which way it flows. This is in chapter 30, so it deals with Faraday and Lenz's law. Whenever we have current going in this direction here, we can use our second right-hand rule, and we see that the magnetic field comes out on this side, and it goes back in on this side. So we do have current going through the loop, but because the flux is not changing, there is no induced current. When we stop it, so when we cut it here, there is no more current flowing. So we went from having current to not having current. The wire is going to cause a magnetic field such that it opposes that change. So we lost the dots, so it's going to give us some dots inside of our loop here. So I should have drawn that better, because whenever the current is going in this direction here, it's producing the magnetic field lines going out on the inside, but then going into the page on the outside. But we don't care about what's happening on the outside of the wire, only on the inside. So the answer is the current is flowing in this counterclockwise direction. So if you want to actually be able to figure out what the value of this current is, you need to figure out what the induced EMF is. This is not necessary to solve this problem because it's just saying, like, explain why the current is induced. So then you just pull out Faraday and Lenz's law. But I kind of want to take it a step further and calculate the EMF that's induced. By Faraday's law, we had E is equal to negative d phi b over dt. Let's say they said that it took 2 seconds for the current to go from something to 0. To calculate the EMF, we then have to figure out what delta phi b is over delta t. We say delta t is like, I forgot what I said, like 2 seconds. Delta phi b is equal to phi final minus phi initial, where initial is before we cut it and final is after we cut it. Remember that once we cut it, there is no external flux because there is no more current here. So so phi final, that's just going to be equal to 0. So 0 minus, we have a minus sign and a minus sign. That means the induced EMF is equal to phi initial divided by delta t. What was the initial flux? So that's our question here, where we look back at this scenario and we want to figure out how many field lines were actually going through the square. It's a bit of a trickier question because we know the field lines are strong here and they're weak down here because that's how it works, right? It depends on R, where it's like the closer you are to the wire, the stronger it is, the further away, the weaker it is. So what we're going to have to do is actually integrate by dividing up our square into these little chunks, rectangles, and saying, well, how much does this contribute to the total flux? So to do that, we need to figure out how far away is it from the wire. So that's R, where R is how far away from the wire is this. I'm going to call this Y, where Y goes from 0 to Y is equal to S. R is then equal to S plus Y. When we talk about flux, we have to talk about area. So here we're going to talk about the area of that little rectangle, dA, and that's going to be equal to S times dy, where dy is just how wide is this. So because we're integrating, dy is going to 0. So next, we just need to figure out our equation for B from the infinite wire, which is just mu naught I over 2 times pi times R, and that is going to be mu naught I over 2 times pi times S plus Y. Our flux is going to be equal to essentially B times dA, so the integral of B dA, because the dot product can go away like it always does, because here we have our area vector pointing in the same direction as our magnetic field. So we have integral of B dA. This is going to be the integral from y goes from 0 to s mu naught I over 2 pi s plus y times dA, which is s dy. So that means the flux is equal to, let's take out all of our constants, 0 to s, 1 over s plus y dy. So the solution to that integral is the natural log of s plus y. So again, we're going to write it out, ln s plus y as y goes from 0 to s. When y is equal to s, we have ln 2s. When y is 0, we have ln of s. ln 2s minus ln s is just equal to ln of 2. So then our flux is equal to mu naught I s over 2 pi times ln 2. So that is the flux through the square when we have current of value I going through our infinite wire. So then here what we'd have to do is plug this value into your equation for the EMF. I guess I wrote it here a little bit better. And then we just need to divide it by delta t. We're not given delta t, maybe you are, maybe you aren't, but this is essentially how you would solve this type of problem. The last question, I didn't know if I wanted to include it, like it was in the exam, but I know some profs don't really cover the material from week 12 or like from the last chapter of the textbook. So maybe you won't see this, maybe you will. I'll just cover it. You have a laser with a beam diameter of 1 millimeter. So that means here, let's draw out our laser. This is 1 millimeter. And it generates an electric field having an amplitude of 0.7 megavolts per meter at the target. What does the amplitude be? These questions are more just figuring out what equations do you need and plugging the values in. So this is B max is equal to E max divided by the speed of light c, which is just going to be 7 times 10 to the 5 volts per meter divided by 3 times 10 to the 8 meter per second speed of light. That's going to give us 2.3 times 10 to the negative 3 Tesla. The intensity of the laser is going to be I. So this is not current, it's intensity. And it's going to be E squared max, which you're given, divided by 2 mu naught, which is the constant that we have seen before. It's 4 pi times 10 to the negative 7. So we get 7 times 10 to the 5 squared divided by 2 times 4 pi times 10 to the negative 7. I'm not keeping my units, and I know I should. Well, you should. I don't have to. But essentially, it's 6.5 times 10 to the 8 watts per meter squared. The reason I don't really care too much is because I know that these equations work, and I know that the intensity has a certain unit, watts per meter squared. And essentially, if you make sure that E is in the right units, mu naught is in the right units, everything is going to work out at the end. So that's what we get for the intensity. The power is going to be equal to the intensity times the cross-section area. So here we have a 1 millimeter diameter. So then this is going to be 6.5 times 10 to the 8 with those units, times the area, which is pi times r squared, which is 0.5, times 10 to the negative 3 meters squared, which is 511 watts. So again, not a really interesting question at all. It's more just like finding your equations and plugging it in. So I'm going to be posting maybe 1 or 2 more practice exams, and hopefully they will help you.